Alright guys, welcome to LIL P Mastermind Tutorials. I am LIL P of BCH, and today we'll be solving 30 questions on EKSU Physics 102. Let's get right into it. So question 1 says, find the force on a 50 centimeter long wire carrying a current of 10 ampere in a uniform magnetic field of 0.35 Tesla if the wire lies at an angle of 60 degrees to the field. Alright, so this is a typical magnetism question. And how do we solve this question? First, we have to know the formula. The formula is F equals LIL P sine theta. All right, that's the formula. I in this case represents the current, L represents the length, all right, of the wire, and then B represents the magnetic field. All right, so all we have to do here is input our given values, but we might have to convert in some places if needed. Now the current, we're told 10 amperes, so we input 10 multiplied by the length of the wire. In the question, the length of the wire is 50 centimeter. Of course, we have to convert that to meter. If you want to convert from centimeter to meter, you divide by 100. All right, you divide by 100, which gives us 0.5 meters, which gives us 0.5 meters. So that's the length after conversion, 0.5 meter. All right, so this is multiplied by 0.5. Now, multiplied by B, the magnetic field. All right, this magnetic field you can find different names for it, like magnetic flux density, magnetic induction. They still mean the same thing. The unit is Tesla. So in this case, they said the magnitude of that magnetic field here is 0.35 Tesla. 0.35 Tesla. All right, and then you have to include your sine 60, which is the angle provided in the question, sine 60 degree. All right, and then here you can evaluate this using your calculator. You should get approximately 1.52. All right, and now since we are solving for force, the unit is Newton. All right, so that's question 1 done. Just remember the formula for the magnetic force on a current carrying conductor is F equals to ILB sine theta. All right, that brings us to question 2. Question 2 says an air-filled multiple parallel plate capacitor consists of 200 plates having dimension 16 centimeter by 24 centimeter. If the plates are separated a distance of 0.02 millimeter, calculate the capacitance of the capacitor. All right, so first things first, we know that what we are looking at here is a parallel plate capacitor. We have parallel plate capacitor here. That's what we're looking at. All right, so there's a formula for parallel plate capacitor, and when you have a lot of them, the formula for the capacitance is C equals to n minus 1. So n minus 1 now represents the number of plates, n minus 1, multiplied by epsilon naught, all right? That epsilon naught is what you call permittivity of free space, multiplied by the area divided by the distance, all right? Distance apart, not diameter, not distance. So n in this case is number of plates, which is 200. Epsilon naught is a constant which I would require you guys to know, all right? Sometimes they are given in the questions, but if it is not given, you should also know it. It is 8.85 times 10 raised to power minus 12 times 10 raised to power minus 12. And then the unit is farad per meter. That is the unit of permittivity of free space. So let us continue. Now, what do we know? What else do we know from this question? We need the area. We know that area is equal to length times breadth. All right, is equal to, and what are the dimensions given in the question? You have 16 centimeter by 24 centimeter by 24 centimeter by 24 centimeter. But before you can multiply these, let us convert them to SI units. So you have to take it from centimeter to meter. 16 centimeter, if you convert it to meter, you're going to get 0.16, similar to what we did earlier, where we divided by 100. All right, so you have 0.16 meter multiplied by 0.24 meter, 0.24 meter. Now, use your calculator, and you're supposed to get 0.0384 as the area. 0.0384. And what's our unit of area? That's meter squared. All right, meter squared. Now what else? We have the distance. The distance from the question was given to be 0.02 millimeter. 0.02 millimeter. But of course, we know we have to convert this to meter again. And how do you convert from millimeter to meter? You just divide by 1000. All right. So on conversion from millimeter to meter, now we are going to get 0.00002. 0.00002. All right. And this will be in meter. All right. So everything we need now, we have isolated them, and then n is equal to 200. So this means we can then input our values. So C will be equal to, now n minus 1, that's 200 minus 1, that is 199. All right, 199. Multiplied by epsilon naught, which is said is 8.85 times 10 to the power of negative 12. Times 10 to the power of negative 12. Multiplied by our area, which we got to be 0.0384. And then divided by the distance now, which we got to be 0.00002. All right. Now, using your calculator, punch this into your calculator to get your answer. Please make sure you do this step. Even though I'm going to provide the answer, you have to confirm if you can actually use your calculator to get the answer yourself. So approximately, our answer is 3.4 times 10 to the negative 6 farad. All right, the unit of capacitance is farad. But we are done here. But look at this 10 raised to the power 6. Do you remember what we call it? This is also called mu, which is micro. So we could have just said the answer is 3.4 microfarad. All right. So that's another way you can find the final answer there. So these two answers are correct. That brings us to the third question, which says a wire having a resistance of 6 ohms, a wire having a resistance of 6 ohms per meter. All right. So basically, you remember that the unit of resistance is ohms, not ohms per meter. All right. But in this particular question, we are using ohms per meter, that is per meter of the wire. It's to be used as a heating element in an appliance that draws a current of 4 ampere from a 220 volt household voltage. How many meters of the wire are needed? All right, so we need how many meters of the wire? The first thing we'll do, let's use Ohm's law. V equals IR. V equals IR. Now, we are looking for the resistance now, so we can make R subject of formula. So if you make R subject of formula, this will give you R equals to V over I. V over I, which is equal to, the voltage here is 220, 220. And the current from the question is 4. So we have 220 divided by 4. Now what is 220 divided by 4? You're supposed to get 55 ohms. 55, 55 ohms. Now that is 55 ohms. Now think about this. If one meter of the wire has a resistance of 6 ohms, and we're looking for a total resistance of 55 ohms, that means if 1 meter is 6 ohms, then 2 meters has to be 12 ohms. 3 meters has to be 18 ohms. So we keep multiplying, right, until we get to this 55 ohms. But how do we get the length now instead of just multiplying until we get to that number? We can say the length of wire needed now, the length of wire is equal to the resistance, which is 55 ohms, our measured resistance, the resistance, over the resistance per meter, which is 6 ohms per meter. Now, one thing that can serve as a check on your work is units, all right, unit analysis. Now, if you look at this, ohms is going to cancel ohms from here. And then when the meter comes up, it is just going to be left with meter, and which is a unit of length that we are solving. That means we are doing the right thing. All right, so 55 divided by 6, this gives me 9.2. All right, so our final answer is 9.2 meter. That brings us to the fourth question. The fourth question now says the magnitude of the magnetic force on a charge particle Q, or on a charge Q moving in a magnetic field B with a velocity V parallel to the field is given by dash. First, we write out the formula. This is the formula that you need to know. This formula for a charge particle moving in a magnetic field B. The formula is Q for the charge of the particle, V for the velocity of the particle, B for the magnetic field now, and then sine theta, which is a factor of the angle. All right, sine theta. Now from the question they said parallel. Now if they are parallel now, that means the angle between them is 0. So this becomes Q V B sine 0, sine 0. All right, and sine 0 is 0. So you should know where I'm going with this calculation. That means everything here turns to 0. That means the force now is 0. Our correct answer is option B. But this is the formula. All right. Now that brings us to question 5. Question 5. The force on a current carrying conductor can be calculated using dash. The force on a current carrying conductor. This is also from magnetism chapter. We did it in the last class on Thursday. All right. So F is equal to I L B sine theta. All right. This is for the angle between them. Sine theta. Right, which is basically the same as this ILB in option B in this question. All right, so that's a very quick one. That brings us to the sixth question. The sixth question says a coaxial cable of length 2 meter consists of a wire of diameter 1 millimeter and an outer shell of diameter 3 millimeter. Find the capacitance of the cable. Now, when we talk about capacitors, basically we say that there are 3 types, which is what we've taken in class. We said parallel plate capacitor, cylindrical capacitor, and then the spherical capacitor. This question is dealing with a cylindrical capacitor. It is dealing with a cylindrical capacitor, and the formula for capacitance of a cylindrical capacitor now is 2 pi epsilon naught 2 pi epsilon naught L over the natural logarithm, ln, or you say logarithm to the base e, anyone you find or anyone you like, still the same thing, into b over a. All right. Now, what is b? What is a? A is the smaller radius. A is smaller radius, and then b is the larger radius. So this tells us that a is less than b. All right. So let's try to isolate our parameters now. A, the smaller radius. Of course, we know we are going to get it from this 1 millimeter diameter. All right. Now, how do you get radius from diameter? Diameter is just twice of radius, right? So radius is diameter over 2. All right. Now the diameter over 2. Now what's the diameter given? They said 1 millimeter. 1 millimeter. 1 millimeter. If you divide this by 2, divide 1 millimeter by 2, you should get 0.5, right? 0.5. But this 0.5, you have to convert it to meters. So let's just do it in one step. So you have to multiply by 10 raised to the power minus 3. That's the same as dividing by 1,000. So 10 raised to the power minus 3. And then the unit is meter now. Let's get B, the larger radius. All right, so B is also equals to the diameter over 2. That's the second diameter, the larger one. So D over 2. Now what's D in this case? D in this case happens to be 3 millimeter. So that's 3 over 2. We can just solve that directly. 3 over 2 is 1.5. 3 over 2 is 1.5. Now we convert that to meter. So instead of 1.5 now, I'm going to have 1.5 multiplied by 10 to the negative 3. Negative minus negative 3. All right? Meter. So this is basically correct. We have A and B. What else do we need? Epsilon naught. Recall that we used it the other time. Epsilon naught, the value remains the same. You have to make this stick. All right? You have to cement it to your heart. So this is 8.85 times 10 to the negative 12 times 10 to the negative 12. All right. So we can input our values now. C is equal to 2 pi 2 pi, our value of epsilon, 8.85, 8.85 times 10 times 10 raised to power minus 12. All right. Then multiply by the length. You see there's still length in this numerator. What's the length from the question? 2 meters. So multiply by 2. Everything divided by ln, or the natural logarithm of b over a. Now what's b over a? That's 1.5 times 10 raised to power minus 3 divided by 0.5 times 10 raised to power minus 3. If you notice this properly, that is just 3. When you solve that, you're going to get 3. All right. So from here, you punch in your expression into the calculator, and you have to get your final answer, which should coincide with mine. All right. So my final answer is 101.2 times 10 times 10 to the negative 12. So of course, what's the unit again? Farad. And that's our correct answer. 101.2 times 10 to the minus 12. That's option A. All right, so we can proceed with the question, which is question 7 now. Question 7 says that is defined as a vector whose magnitude is the electric current per cross-sectional area at a given point in space. The answer is current density. All right, current density. Current density. I'll give you the formula now. Current density. If you notice what this thing looks like, what I'm writing, please know that I'm using my finger on the trackpad of the laptop, so I do not have a stylus or any pen yet. So it is very hard. So current density, that is the answer. The current density is noted J, all right? So I'm going to put an arrow at the top to show that it is a vector. So J is equal to I, which is the current, over A, as defined in the question, current per cross-sectional area. Now what do you think the unit to be? The unit is just ampere per meter squared. Sometimes these things are so simple. But most times they are simple. All right, so that's question 7. That brings us to question 8, which says that is defined as a vector. All right, so we've done this. That's repeated. Which of the following is the characteristic of electric charge? All right, so we are asking that which of this is true as a characteristic of electric charge. So the first option, they said electric charge does not have a polarity. That is wrong. Why? Because we know electric charge has a polarity. It is either positive or negative. All right. The second one, electric charge is conserved. Yes, this is a statement in the properties of charge where we say conservation of charge. Charge can neither be created nor destroyed. Now let's evaluate the third one and see why it's not correct. This one says electric charge is not quantized. The correct statement is that electric charge is quantized. And what does that mean? The charge, all right, on anybody would always be an integer multiple of the elementary charge E. All right, so this statement is also wrong. Of course, this one is wrong too. Therefore, our correct answer is option B. Electric charge is conserved. Now let's move to question 11. Question 11 says that the resistance of a copper wire of 5 meters is 0.5 ohm. If the diameter of the wire is 0.045 centimeter, determine its specific resistance. Now, what is specific resistance? When we say specific resistance, we also mean resistivity. That is another name for resistivity. Please don't be confused by our choice of words here. So resistivity is the same as specific resistance. Now, what's the symbol for resistivity? That is rho, the Greek letter rho. That letter that looks like P with curved leg, outward curved leg, something like this. Rho. All right. That is rho. That is resistivity. But to get the formula, let's start from our basic formula for resistance, which we all know. R, the resistance, is equal to rho L over A. All right. That is the formula for resistance. Now, if I want to make rho subject of the formula, I have to cross multiply in such a way that I'm going to have rho is equal to R A over L. All right. R over L. So we have to input our values now. But some of these values still have to be converted to standard unit. What's our resistance? 0.5 ohms multiplied by the area. We know the area is not present in the we're not given the area, we have to evaluate that ourselves. The length is given to be 5. Now let us calculate our area. Radius is equal to diameter over 2. Of course, I can use the diameter directly in the formula for area by using 1 over 4 pi d square. But let's not get into that. Let's just follow our traditional method. Did I just say traditional? 4, 5. Divide by 2. All right? Divide by 2. Now you should get 0.0225. 0.0225. That is what you should get. Now, after getting this 0.0225, what should we do next? What should we do next? The next thing to do is to divide by 100 to convert it to meter. Of course, I'm just going to do that directly. If I do that directly, I'm going to get 2.25 times 10 raised to power minus 4 to be my radius. 2.25 times 10 times 10 raised to power minus 4. All right. Now this is in meter. Now I can go ahead to calculate the area, which is pi r squared, which is equal to pi open bracket r radius, which is 2.25 times 10 to the negative 4 meter, and then squared. And on evaluating that using the calculator, you are supposed to get 1.59 times 10 to the negative 7 meter squared. All right. So we can then input this into our calculation from there. So we are going to have times 1.59 here. 1.59 times 10 And our final answer should be 1.59 times 10 times 10 to the negative 8. Negative 8. Now, what is the unit for unit of resistivity? That is ohm multiplied by meter. Ohm multiplied by meter, so that's 11. Now, the first question says calculate the capacitance of two plates of area 4 centimeters squared separated by 1 millimeter. Take here the permittivity has been given. Of course, since we are dealing with parallel plate capacitors now, the formula remains the same: epsilon naught A over D. All right. So let's input our values for 8.85 times 10 to the negative 12. The area, which we are still going to calculate, we're going to convert. And then the distance is 1 meter now. So if you convert that to 1 millimeter, if you convert it to meter, now you're going to have 1 times 10 minus 3. All right. So let us get the area now. The area is equal to 4 centimeters squared. Now, how do you convert from centimeter squared to meter squared? So it's kind of similar to what you do when you want to convert from normal centimeter to meter. You divide by 100, right? So put it here, divide by 100. But square it. So the same thing occurs when you're trying to convert from centimeter cube to meter cube. You divide by 100, then you cube it. All right. So here you should get your value to be your value for 4 divided by 100 raised to the power of 2. You should get 0.0004. 0.0004 meter squared. Meter squared. Right? So we can input it here. 0.0004. All right. And then on solving this, we are supposed to have as our final answer approximately 3.54. 3.54 times 10 to the power of negative 12 farad. All right. But what is 10 raised to the power minus 12? That is pico. All right. So this becomes 3.54 pico farad. 3.54 pico farad. That's option B. All right. So the next question says a circular wire loop of radius. A circular wire loop. A circular wire loop of radius 12 centimeter. Radius 12 centimeter carries a current of 1.5 ampere. If the wire is placed in a magnetic field, B equals to 2 Tesla, calculate the magnetic moment that can occur on the loop. Now, the formula for magnetic moments, this is also from magnetism in physics 102 magma, what we did in the last tutorial in school. All right, is equal to current multiplied by the area. Current multiplied by the area. Of course, we have the current already, which is 1.5 ampere. The area is what we are going to try to get now. All right, so to get the area, we calculate, we use pi r squared. Pi r squared. All right, so equals to pi. What's our radius? The radius is not given in meter, so we convert to meter. 12 divided by 100 is 0.12. Right, so we can quickly do that without having to write it out again. 0.12, right? 0.12. And then the area should give us 0.0452. 0.0452 meter squared. Meter squared. All right. So if we proceed with this now, you can input this into the formula and have I, which is 1.5, multiplied by the area, which is 0.0452. All right. And when you solve this, you should get 6.8 times 10 to the negative 2. So what's the unit? Since we multiplied current by area, the unit should be ampere meter squared. Ampere meter squared. All right, let's proceed. That brings us to question 14. A wire of diameter 1 millimeter carries a current of 20 ampere. What is the current density in the wire? If you recall, we introduced the formula for current density in a previous question, where we say the current density is equal to I over A. I over A. So we already know the current I in this question, but we don't know the area. So we have to solve the area. The diameter is equal to 1 millimeter. So the radius is equal to the diameter over 2, which is 0.5 millimeter. All right. So this, when we convert it to meter, of course, you just multiply by 10 raised to the minus 3, or you say you divide by 1,000. 0.5 times 10 to the negative 3 meter. All right. So your J now, your current density, will be equal to 20 divided by the area, which will be pi, open bracket, 0.5 times 10 to the negative 3 squared. All right. And that should give us, on evaluation using the calculator, that should give us the area to be 7.85 times 10 to the minus 7. 7 point. Please make sure you're confirming the calculation with your own calculator, because I could be mistaken and make a mistake anywhere. So 7.85 times 10 to the power of minus 7 meter squared. All right. So I can just input it at 7.85 Therefore, J is equal to, the final answer should as be 2.55, 2.55 times 10 to the power of 7 or 7 ampere per meter squared. That brings us to question 15. The potential difference across each capacitor in parallel connection is dash. The answer is the same. So in your notes, what I want you to do is write heading capacitor, all right, and then in a tabular form, write in series in one column and then in parallel in the other column, and then compare and contrast each of these properties like the voltage, the current, the charge, all right. So tabular form like this, series on this side and then parallel on this side, all right. So you can understand what each of this is. Now the space between capacitors contain an insulator called dash. All right, so we usually use an insulator between the plate of our capacitor. It's mostly, sometimes we leave it as air or vacuum, or we use a particular insulator in here. This insulator is usually called dielectric, all right? The dielectric, all right? And each dielectric has its own dielectric constant. It has its own dielectric constant. That's the answer to question 17. Question 17 says, that is defined as the net rate of charge flow, or the net charge flow per unit time, all right? The answer, of course, here is current. Because I, when you have uniform flow, of course, is equal to Q, which is the charge, over T, when you have uniform flow. Right, so the correct answer for this question is option B. Right, let's move to the next, which says find the conductivity of the wire if the resistance of a 100-meter long wire is measured to be 8.2 ohms and the radius of the wire is 0.04 ohms. What I'm going to do first, I know I'm going to have an issue with area and conversion later, so I'm going to solve it first. So area is equal to pi r squared. All right, so I still have to convert the radius from centimeter to meter. And how do you do that again? You divide by 100. So if you divide 0.04 by 100, you should get 4 times 10 raised to the power minus 4. 4 times 10. 4 times 10 raised to the power minus 4. And then we square that. So the area, on solving that, we should get the area to be 5 times 10 to the power of negative 7 meters squared. 5 times 10 to the negative 7 meter squared. That's the area. All right, so since we've cleared that, let's try to calculate our conductivity. Please, let us follow a flowchart to that formula for conductivity. I don't just want to give you the formula, I want to show you how to get it. So let's start with resistance. Resistance, as we said earlier, is what? Rho L over A. Now, what is rho again? Rho is the what? Is the resistivity. So if you make rho subject of the formula, you're going to have rho is equal to R A over L. Now, there's a particular thing which is the reciprocal of this resistivity. That is 1 over resistivity. That thing is called the conductivity. So please note, conductivity is the reciprocal of resistivity. In a situation where you're given the value of resistivity and we ask you for conductivity, all you have to do is 1 over that given value. All right, so if you do 1 over rho now, this means you invert this formula to become L over R A. All right, L over R A. I can then proceed to input my values. If I put the values for length, the length is 100 meter. 100 meter divided by the resistance, which is 8.2 multiplied by the area, which we solved at the beginning, to be 5 or 5 times 10, 5 times 10, 5 times 10, 5 times 10 to the negative 7 meters squared. So we should get a final answer for conductivity to be equal to 2.44 times 10 to the power of 7. Now, what do you think the unit would be? Now, since the unit of resistivity is ohm meter, and this one is reciprocal of resistivity, therefore the unit of this one should be per ohm per meter. All right, that's the final answer. All right, that brings us to the next question, which says find the conductivity of the wire, blah blah blah. Just of that. Next, using KCL. What is KCL? KCL is Kirchhoff's current law. All right, so that's the first law. Kirchhoff's current law. This is the spelling of Kirchhoff. Now, what does Kirchhoff current law state in simply put? It says that the current entering a junction should be equal to the current leaving that junction. Or in other words, the algebraic sum of currents, all right, passing through a junction is 0. This point here at the center, where this arrow bifurcates, is what we call the junction. All right, so you can just say your formula is summation of current in is equal to summation of current out. So how do you know current in? How do you know current out? Just by looking at the direction of the arrow heads. So this arrow, this one right here, is pointing into the junction. This one right here is also this one. This one here is also pointing into the junction. So that means the currents in are I1 plus I2 plus I2. This should be equal to what's the current out? I3 is pointing away, therefore it is going out, equals to I3. But the question asks us to look for I1. Therefore, we make it the subject of the formula. And how do we do that? We move I2 to the other side where it becomes negative. So this is I3 minus I2. Now, if you look at the question, they said if I2 and I3 are 2 ampere each, so the value of this is 2 ampere, and the value of this one is also 2 ampere. When we subtract that, we get 0. So your answer for this is 0. I1 is equal to 0. All right, so we pick 0 here. So that brings us to the next question, the 21st question. One of the following is a ferromagnetic material. If you remember what ferromagnetic materials are, we've not taken them in magnetism, but we will in the next class. All right, so they can be magnetized strongly. All right, so the answer here is iron, and they have magnetic permeability that is very greater than 1. Find the force between 2 coulomb and 1 coulomb charges separated by a distance of 1 meter in air. What is the formula for these force? The formula for the force is F. This is got from Coulomb's law. F is equal to K, Q1, Q2 over R squared. All right, so that is the formula, and everything we need has been given. Now, what is K? K is called the Coulomb's constant. K is called the Coulomb's constant. Coulomb's constant. Coulomb's constant. Coulomb's constant. And it has a value. The value of K is 9 times 10 to the power of 9. 9 times 10 to the power of 9. All right. This is equal to 9 times 10. Now, can you guess what the unit is? To know the unit, if you don't want to cram the unit, just make K the subject of the formula from this expression, and then you put the units of the remaining quantities. On doing that, you're going to realize that the unit is actually just Newton meter squared per coulomb squared. It is like that. All right, so 9 times 10 to the power of 9 Newton dot meter squared per coulomb squared. What is this looking so similar to? It is looking like G in the Newton's law of universal gravitation, if you guys remember, from Physics 101 last semester when I taught you. So 9 times 10 to the power of 9 multiplied by Q1, which is 2, multiplied by Q2, which is 1, divided by the distance squared, which is 1 squared. Of course, we just multiply that by 2. And on doing that, we should have a final answer of 1.8. 1.8 times 10 to the power of 10 times 10 to the power of 10. And then the unit is Newton. Simple, is it not? So that brings us to the next question, the 23rd question. The unit of relative permeability. Do not stress yourself here. Relative permeability is dimensionless. All right. So when we say relative, of course, you would expect that it is dimensionless because it will be the ratio of two same quantities. Find the force on a charge of 2 microcoulomb, plus 2 microcoulomb, moving with a velocity of 2 times 10 to the power of 6 in a field of magnetic flux density 0.5 Tesla parallel to the field. Do you know this is similar to what we did earlier? What is the formula for a charged particle moving in a magnetic field? The formula remains the same. The formula is QVB sine theta. QVB sine theta. Now, if you notice, you already know the final answer is going to be 0. But let's just solve it first. What is the charge? 2 microcoulombs, so that is 2 times 10 to the power of negative 6. 2 times 10 to the power of negative 6. 2 times 10 to the power of negative 6 times the velocity, a very fast moving object. 2 times 10 to the power of 6. I know that 10 to the power of negative 6 and 10 to the power of 6 are going to cancel out here. I'm going to be left with 2 times 2. All right. And B, what is B? 0.5. 0.5. And then sine 0 in this case because it is parallel. Sine 0, and everything collapses back to 0 Newton. All right. So that's the answer A. Now let's go to the 25th question, which says calculate the energy stored in a capacitor of capacitance 20 microfarad if the potential difference between the plate is 40 volts. Between the plate is 40 volts. Now, how do we solve this? What is the formula for energy stored in a capacitor? The formula for energy stored in a capacitor, there are actually 3 formulas you need to know. And we mentioned the 3 formulas in class. You can just quickly check your notes to confirm them. I also told you how to derive them. The formula is half CV squared. C being the capacitance and then B being the voltage or potential difference. So let us input C, which is 20 times 10, 20 times 10 to the power of negative 6, because that is what micro means. And then multiplied by our voltage, which is 40 squared. 40 squared. Now let's not forget the half that we have outside. 1 over 2 is just 0.5. 0.5. Alright. And on solving this, we should get a value of 1.6 times 10 times 10 to the power of negative 2. Now what's our unit? Because we're calculating energy, so this has to be joules. So E is equal to joules. Alright, 1.6 times 10 to the negative 2 of joules. Let's take this question. Compute the magnitude of the magnetic field of a long straight wire carrying a current of 1 ampere at a distance of 1 meter from it. Alright. So this is a very interesting aspect of magnetism too. So in this, I mentioned in class on Thursday that in this magnetism, you should be able to calculate a magnetic field pertaining to different arrangements, or let's say mass now, alright, or body, yes. So for a long straight wire, this is the formula: mu naught over I divided by 2 pi r. I said you're also going to learn for a coil, a solenoid, and then a toroid. You are going to need formulas for those. But since we are limiting our class to this, we are going to take just this one, and then in the next class, in the subsequent classes, I'm going to introduce the remaining formulas for the toroid, the solenoid, and the coil, and the n turns of coil. Alright, so mu here, what is mu? Mu is what you call permeability. So very similar to what we have in electrostatic, which is permittivity. Here it is called permeability. Permeability, alright, of free space. It has its own value. It does the same way the permittivity has its value. Now, what is the value of permeability? The value is 4 pi. Yes, it has a pi in it. 4 pi times 10 times 10 to the negative 7. Negative 7. All right. Negative 7. Henry per meter. That's the unit. All right. So B, let's input R. parameters now. B is equal to 4 pi times 10 to the negative 7 multiplied by the current I. The current in this question is just 1 ampere. All right, so we have 1 ampere divided by the 2 pi r. Please note that r in this case is not the radius, it is the distance to the current carrying wire. Right, so not radius, do not divide by 2. Now multiply by r, and then from here the question says distance of 1 meter from this. I'm just going to use 1 meter. All right, so 2 pi cancels 4 pi here. You're going to be left with 2. All right, so the final answer now you just multiply 2 by that. I'm going to get 2 times 10, 2 times 10, and now we still have 2 times 10 to the power of negative 7 Tesla. I hope so. I think the question is a bit wrong because instead of 1 ampere, we're supposed to have 10 ampere and use it this way. So let us proceed. Let us proceed. So a similar question where we have 10 ampere. So we ask to calculate magnetic induction at the point perpendicular at the perpendicular distance of 0.5 meter from the wire. Do not be confused with the words. Magnetic induction, like I said earlier, is another name for this magnetic field or magnetic flux density. Anyone wants to call it. Alright? So it is still the same thing. We are still using the same formula since we are dealing with a straight wire. Alright? Now you should know that the formula is actually mu naught mu r I over 2 pi r. But since they did not mention a medium here, we're going to assume air or vacuum, and then mu r from that is 1. That is why it is not in these formulas. So we're just going to keep using this simplified formula. And if you encounter a question where a medium with a specific relative permeability is given, then you have to input it into the formula here. Right, so let's proceed. 4 pi times 10 to the power of negative 7. Right, divided by I, which is 10, divided by 2 pi, divided by r. But this starts with 0.5 in this case. So let's do these together. So 2 pi cancels 4 pi. You're going to be left with 2. Now, 2 divided by 0.5, that is going to give you 4. Now 4 times 10, that gives you 40. Alright, so you have 40 times 10 raised to the minus 7, or you can just say 4.0 times 10 raised to the power of minus 6. The final answer is 4.0 times 10. Hope you guys know that Tesla is actually a big unit. 1 Tesla is actually a big unit. But most times you get raised to the minus something Tesla. Alright. Now the next question here, a long straight wire has a current in it. A long straight wire has a current in it, right? At a particular distance of 0.05 from the wire, the magnetic induction caused by the current is 0.000002 Tesla. Alright? Calculate the current in the wire. So of course this thing is twisted a bit, but it's still the same question. We're still dealing with the same wire, so we have to use mu naught I over 2 pi r. But in this case, you can notice that we are looking for I. So we have to make I subject of the formula. So you are going to be left with I is equal to, I believe you guys remember to make something subject of the formula. So B 2 pi r over mu naught. Alright, that's what we are left with. That's the formula. So alright, so let's proceed. Let's input our values. What is B from the question? 0. As you can see, very small again. 0.000002 Tesla. Multiplied by 2, multiplied by pi, multiplied by distance from that wire, which is 0.5 or 0.05 meter, and everything divided by the permeability, which is 4 pi times 10 to the negative 7. Alright, because I know that 4 pi here, I'm going to be left with 2, and then here it's going to be cancelled. Alright, and then I can just evaluate this to get the final answer, which is 5, just 5 ampere. 5 ampere. Please make sure you confirm that with your calculator. Now the 29th question, this is somehow long, but it says a straight conductor of length 25 mm is placed in the uniform magnetic field of magnetic induction 0.70 Tesla. There is a current of 2.0 in the conductor, and the conductor experiences a force of 9.5 millinewton. Calculate the angle between the direction of the magnetic field and the conductor. Alright, so you're going to have F, using a slightly different formula here. F is equal to what? Since we are talking about the conductor here now, we're going to have the same formula, ILB sin theta. ILB sin theta. Alright. Now, what are we looking for? We're looking for theta. So first we can say that sin theta, is equal to F over I, L, and then B. Alright. Now theta is what we're looking for, so we have to say theta. Now when sine goes to that side, it becomes sine inverse, right? Arc sine. So you have sine inverse of F over I, L, B. Alright. So this is equal to sine inverse. Let's just input our value. What's the force? They said 9.5 millinewton. Milli is just 10 raised to the minus 3, so you have 9.5 times 10 to the power of minus 3, all right, divided by I times L times B. I wonder if this parenthesis will be enough. So we have 2.0 for I, that's the current, multiplied by the length, which we said is 25 millimeter. After converting 5 millimeter to meter again, that is dividing by 1000, dividing by 1000, that should be 0. Should be 25 times 10 to the power of negative 3. Alright, so we have to rub off that parenthesis there, because this will not be enough. Good. Alright, so let's proceed. That is for the length. Multiplied by the field now. The field strength, which is 0.70. 0.70. Alright, so this gives us a final answer of 15.75 degrees. So this is just a few out of the question bank that we are working with, like the questions we are about to solve, that we have to solve this semester. And so we continue dropping things, continue solving them. Now this last question says, stretch the magnetic field lines around the following arrangement of permanent magnets. Now one thing you should know about the magnetic field lines, which is similar to the electric field lines, is that the lines come out of the north and enters the south, all right, and they form a closed loop, unlike electric field lines that don't form a closed loop. So whatever you want to draw now, you want to make sure that it comes out of the north and enters the south. So basically, this is what you are looking to draw. Oh my god, that's the worst looking curve. I do not know if I have a curve function. I'm going to try again. It's going to be hard, but I'll try it. Alright. Off to a good start. Good. And let's just try to do this. Anyway, turn out. We're going to use it. Alright. So how do you show that it's coming out from somewhere and entering somewhere? You use arrows. Alright. So here you just leave 2 out. And then here 2. So we said it has to come out of north, so you have to draw your direction of the arrows this way. So it shows that it's coming out of north. And it has to enter the south here, so the arrows point here. All of these are entering into the south pole here. Remember these are called poles. And we said monopoles do not exist. You remember we said in the last class that a north pole is usually associated with a south pole. Unlike charges, where you can have a positive isolated charge and then a negative isolated charge. Alright, so let's draw for these two. This is coming out of the north. Same thing happens here. So this is a pretty good diagram, but of course if you try it in your notes, it's going to be better. Now let's see this. We have north and north close to each other. We know they are going to repel, so the magnetic field lines is going to look something like this. It's going to look something like that. Alright. So it will still come out of the north. And then of course it is still going to form a loop around itself. Right? So it is still going to form something like this. Deeply apologize for this diagram. I'm using my finger on the trackpad. It is very hard to do. So we hope to get a pen, a stylus very soon. Alright, so now we show the direction that it is coming out of the north and entering the south. Sorry, it should be in this direction. Same thing here, out of the north. And that brings us to the end of the tutorial today. My name is LIL